Here, do you hear this? Here, listen to this, real quick. Yeah. You hear that? Those are ice cubes chilling in a glass, crackling. And I've been in the house too long with the kids and the in-laws, and they finally left. Well, the in-laws left. The kids still here. Anyway, I'm gonna have a sip. I'm very parched. Anyway, oh, let's do this. I'm snowbound. It's crazy outside. I have no idea what the hell's going on anymore. Okay. Tosylates, mesolates, triflates. All right, so we were talking about this when we ended off the lecture last time, and we use tosylates and these things to, when we want to make alcohols better leaving groups. Why? Because OH is a horrible leaving group in an SN2 reaction, so we have to convert the OH to a better leaving group somehow. Okay, this is one of the ways to do it, is to take your OH, convert it to an O-tos or an O-mesolate, and it will be a better leaving group, because as it leaves, as the nucleophile comes in and kicks off the tosylate or the mesolate, this O group here, which was formerly on the OH, right, is now on the O-tosyl or O-mesyl here, and this is now engaged in resonance. So this resonance here can be, well, let me just see if I can get on to do some pen work here. Have some lone pairs. Lone pairs. Alright, lone pairs here, there, and there. And you can dump those lone pairs into there, and so forth and so on, and have all kinds of nifty resonance to make this a great leaving group. Okay? So, sample mechanism for sulfonylation. Alright, so you want to sulfonylate something. You want to tosylate something. Let's just do a typical thing. You have we'll use ethanol. All right, there's that. So cheers. All right, so take that guy here, and we use for sulfonylation, like for tosylation or mesylation, or even triflation, we use the chloride version of this. Okay, so you take a tosyl group, a tosyl chloride, which is going to be your, pardon the drawing, I'm using this drawing pad on my lap here, and my lap is, I don't know what the hell's going on with my lap. Alright. There's that. That's wrong. That's completely wrong. So let me erase. Can I use an eraser? I don't know if I have an eraser. I have an erase pen. Does that work? Oh, well, thanks. That's nothing. Okay. Alright, let me try this again. Alright, take 2. Alright. I got so crazy about the chloride talking about it that I just ignored science. There you go. Sulfonyl. This is an S. Alright, there's your chlorine there, and this is a tosyl group, so we're going to put a toluene. So, para-toluene sulfonyl chloride, or tosyl chloride. We usually use tosyl chloride with pyridine. Alright, you take your benzene ring there, and put a nitrogen right in the benzene ring. And there's your lone pair for that. So this is pyridine and tosyl chloride, roughly in a 1-to-1 mixture. 1-to-1-to-1 mixture, roughly. Okay? So what's the mechanism? Pretty straightforward. It's not a not an SN2, not an SN1. It's like an addition elimination. So now you're adding your oxygen here. You're attacking from your oxygen to your sulfur. That is going to kick that up. All right? Now let's just draw our intermediate here. Alright, that's the oxygen there. There's your hydrogen there. Your new bond here is your sulfur. And let's just try to combine everything that we've done so far. So there's your O- from there. There's your double bond. Still there. There's your chlorine. Alright, still attached. Alright. And there is, and I'm going to abbreviate this, so I don't have to keep on drawing it. I'm going to abbreviate this toluol, or TOL. Right? This is for the toluene group. TOL. Alright, so there is this intermediate. Okay? Oopsie, forgot this charge. Remember, you keep, if it's a neutral species to begin with, or a set of them, keep them overall neutral. Even though these are charged separated, they are still a negative and a positive when you add them together, are still going to be a neutral species. All right, so you have that species right there. All right, which then you can then collapse down to get rid of this chlorine here. Right, so this guy here will swing on down. So I'm trying to draw in the lone pairs with this pen, but it's hard. All right, so there. All right, this will kick off this chlorine. You say, well, wait a minute. Why did you kick off the chlorine? You could have just kicked off the OH plus. Well, if you do that, then you're back to this. Then you're back to starting materials, and that's not productive. We want to be productive. We want to go forward in the reaction. So even though there is, I am sure there is a little bit of reversal. I am sure this is acid-base chemistry. So why wouldn't there be a little bit of reversal, right? But since we have the ability to have some reversal, that's fine. We understand that. But let's go forward and assume that we have a reaction that is a positive thing that actually occurs. That's a good. I should drink this more often. All right. All right, good. Let's do this. Now let's always keep track of what we're getting rid of and stuff. Okay, so we're getting rid of that chlorine. So we're going to hit this with a minus Cl, right? Minus Cl must, because when chlorine leaves, it's going to leave as a chloride ion. All right. Sulfur. Your original double bond from there, your newly formed sulfur oxygen double bond right here. The chlorine's gone, but the toluene is still there, so we'll say tol. No, I'm tol, T-O-L. Notice that this is a tol group, T-O-L group, tol group, but this whole thing is a TOS. This is a toluene here, but this is a toluene sulfonyl, or a TOS group. All right, so this is a tol, but this is a TOS. This whole thing here is a TOS. All right, we still have this here to contend with. All right, and now of course we have still a system that looks like it's inbalanced for charge, but we have a minus here and a plus here, so it is actually pretty still balanced. All right, but we still have this charge to take care of here because we don't want this species here being that higher energy, right? So we're going to have our handy little chlorine here that's just floating around. Cl minus will come in and rip off that proton right here, giving us our. I'm just going to draw O. I'll draw it mostly out. Tall. Okay, this whole thing here, I just want to remind you, this is a TOS group. All right, plus HCl. Now the important part is here's where the pyridine comes in. This pyridine here, your book says that the pyridine comes in here, pulls off that proton, and does all kinds of hijinks, or it pulls it off here or here. Either way, I don't like it. It doesn't work that way. Pyridine doesn't abstract protons; it absorbs protons. It's not that strong a base. It's going to absorb. It's going to absorb that acid right there. All right. So let's assume, even though we know this is sort of bullshit, and doesn't have a covalent bond here, we're going to take pyridine. All right, and it's going to zoop. It's going to pull off that proton right there, kick off sort of that, and what you're going to have here is this own little side reaction where you actually have pyridinium. That's a nitrogen. All right. There's your pyridinium, right? Because the nitrogen is protonated hydrochloride. So this guy here is pyridinium hydrochloride, right? Which falls out of solution as a solid. So you have pyridinium hydrochloride and you have this O-tosyl. So why the hell do you need the pyridine here? In case you don't remember from last semester, or if you're new to this class, the reason why you need to have pyridine around is to absorb HCl, because if you don't and you just keep on generating HCl, this HCl will go back and attack your starting material. And you're saying, yeah, but big deal. Why? What does it matter? Well, here's what happens if you attack your starting material. You have alcohol here. Here's what you don't want to happen. All right, you have your alcohol there, right, and then you have your HCl that you made. All right, if you have HCl, this is going to protonate that oxygen of that alcohol, giving you this protonated alcohol. right? Plus Cl minus. Now two things can happen. Thing one that can happen is chlorine can attack the backside of that carbon here, giving you the ethyl chloride. So that's an untoward or an unwanted reaction. That's one way of doing it. All right. But at the very least, when you have this species here, so the one thing is that you have potentially a not a good SN2 type of reaction that you don't really want. So that you don't want that. No one it. All right. Or the other thing is that this guy here should be involved in a nucleophilic attack of that sulfur, but this can't do that because now this is no more nucleophilic. When you're a nucleophilic, you have an excess of electron density to use to be able to attack something, right? This guy here is going to use this partial delta negative to attack this delta positive. It can do that because it's delta negative. This guy here is no more delta negative. It is a full positive. There's no reason for it to want to do any sort of nucleophilic attack because it is all full up. It has no more impetus to be a nucleophile. All right. So this is good here because you have this is the sulfonyl procedure for tosyl, mesyl, or the triflate, I believe, trifluorosulfonyl. All right, so this is all one thing. You just change out the different R groups on the sulfur. Okay, that's all you got to do. All right, so ethers by intermolecular dehydration of alcohol. I'll drink to that again. Every time I'm going to say alcohol, I'm going to drink. No, I don't do that. No, it's still not a bad idea. Okay. Okay, so here's the thing. So you already know how to do this, sort of. Okay. You take your alcohol here and you heat the bejesus out of it in sulfuric acid, and you end up making ethylene gas. All right. But if you don't do that, if you don't heat it up as high as this, and you heat it a little bit lower, you can make acid catalyzed symmetrical ether bonds. Okay, and so you could do that. All right, and so that's just one way to do it. Okay, but there's multiple ways to be able to do this kind of thing. All right, and we'll go over the mechanism in a minute. Okay, and do we have some time over here? Yeah, I guess we'll talk about the mechanism now. Okay, so we will do that. Let's take this ethanol here, heat it up with a little bit of acid and heat, and make diethyl ether. Okay. So take one more, and now here, notice we're not talking about any stoichiometry here at all. We're just talking about as much alcohol as we need to be able to do the chemistry. All right. So let's just do that. You use H plus because we know what sulfuric acid is, and we'll say heat. Now we know what's going to happen here. All right. We're going to do this. We're going to protonate. So like the thing that we didn't want to do last time, we want to do now because we actually want to make some substitution. So we use sulfuric acid, make our protonated. The people in the background are my wife and children my wife trying to bathe the kids. Let's see how that works out for her. All right, she should get some help. Having kids is hard. Anyway, so you have this protonated alcohol over there, right? And let's say another alcohol is floating around. All right. Now this guy here. Now where do I pull this other alcohol from? Because we have enough of this. We have QB. We have QB amount. That is quanto basta. That's Latin essentially for enough. We have enough that we need to do the reaction. All right. We have QB of that. So we're going to protonate 1 mole of it. We're going to take another mole of it, and then have that mole of it attack the back side of that. Kicks that off like so, and gives you your protonated in this case here, diethyl ether, plus your water that's kicked off. Okay, that seems to be pretty efficient, right? That's not that bad. Oh, by the way, then you have to deal with this business. Okay, so let's have our water come on in, pull off that proton right here, right there, and give us our diethyl ether plus. Now no more water, but H3O plus, which is convenient because H3O plus is our catalyst, or our catalyst. Oh Jesus! I'll stop. All right, is our catalyst, right, for this. So we get some of that back, which is then fulfills the role of the catalyst. Okay. So this is pretty good. It's pretty efficient. It's cheap as all hell, which means I love it. But the bad thing about it is that it's limiting. How is it limiting? Well, you have to have, if you want to use this procedure to make ethers, you have to make sure that the ethers that you want to make are symmetrical. That means the left side is the same as the right side. You can't make like an isopropyl on this side and then have an ethyl on that side. It doesn't work that way. You can do that, but using a different method. Okay, but this is this acid catalyzed method is not a bad way to make highly symmetrical ethers. Okay, so that's not a bad thing to do. Okay. Enter in the Williamson ether synthesis. Now this might be somewhat of a review for many of you from last semester, but still we'll go over it again. Okay, the Williamson ether synthesis is a synthesis of asymmetric or symmetric ethers by way of an SN2 reaction, wherein you have one of your R groups here is, let's just say it could be like an alkyl halide or an alkyl tosylate, and one of your other species there is going to be an alkoxide species, okay? And so that guy there can be a nucleophile to attack in to this electrophile over here, because this guy here is very nucleophilic and this guy here is very electrophilic, okay? And so that's how that's going to happen. All right, and this happens via an SN2 reaction. But the R is limited to a primary and secondary, right? Why? Because this is still, even though it's a new name reaction, right? It is still an SN2 reaction, which is still, it still has to fall into the strictures of being an SN2, which means you can't do an SN2 like on a tertiary substrate, for example, So let's just talk about a very simple Williamson ether synthesis. You know what? Let's use a tricky one. Let's make this guy. Let's make methyl terbutyl ether. All right, methyl terbutyl ether. All right, that's an ether. We can't make it by the acid catalyzed method, so we have to use another method that we would use to be able to attach both this methyl side and this terbutyl side, right? Now we can start with one of these alcohols, and I'm going to start off with this being the alcohol. I'm going to start off with terbutanol, right? Terbutanol right there, right? And I say this is going to be the alcohol that we start with, because what happens is that once we have this guy here, we can treat it with a good base, a good strong base. We'll use, in this case here, we'll use sodium hydride. Now I'm not using an ethoxide or an alkoxide base, because the alkoxide bases are, the pKa's are too close to what this would be. So the sodium hydride here is a nice strong base way up there in the pKa range. Okay, and so I'm going to be using that. I'll probably be using a good solvent. Maybe DMF is a good solvent for that, right? All right, and so that's going to do some simple acid-base chemistry. All right, this hydride is going to pull off that proton right there. When it pulls off that proton right there, this pair of electrons will go right back here to the oxygen, making this sodium terbutoxide. All right. This guy here is now going to be a good nucleophile to then be able to add in this other piece here. Now this other piece here, now we can just simply use another alkyl, group here with a good leaving group. Let's use, since we're only going to do methyl, let's just use, I don't know, methyl iodide. That's cheap to buy. And I'm going to see if I can just draw the methyl pretty straight, pretty obvious, right? So you can see. And there's your iodide right there, right? So this tributoxide here, right? We'll attack the back side of that carbon right there, kicking off that iodine right there, giving you your final product plus what? Sodium iodide plus sodium iodide. Okay, so it's acid-base chemistry followed by, and this is where your SN2 comes in. It's right there. Okay, that's where your SN2 is. Right, and so once you have that, this is how you can make your asymmetric ethers. Notice you cannot make this by the acid catalyzed method. All right, but it seems pretty specific that I chose to make this ether, this MTBE, by this method. Well, what would happen if I do the opposite way? What about if I use this as the alcohol to deprotonate? Well, let's try that and see where we end up. Let's use methanol. Same hydride. This chemistry works fine. Right? Okay, so we'll do this guy here. Well, now we'll make sodium methoxide using the same exact method as we did before, right? There's that, all right? All right, so now you have your sodium methoxide. Now, instead of using, now because we've already made this side of the molecule here, what happens if we just use this as the, we'll bring this in as the thing that is the electrophile? Well, I think you see what the problem is, right? What you have right here is that you have an SN2 reaction setup that you'd like to do, but you have a good nucleophile, a good small nucleophile that's very strong and very hard and very willing to do the substitution. But now you have an electrophile, which is a good electrophile, but not for an SN2. Why? Because this is a tertiary substrate, and tertiary substrates do not undergo nucleophilic substitution very quickly or at all. Let's just say, for what we need to. Okay. So as you all know, when you have an SN2 setup, but you can't do an SN2, well, the next best thing is going to be a competing E2. All right, so you will have a bimolecular elimination when this happens. So you have your tributyl iodide that will be attacked, right, in the beta position. This one of these protons here will be abstracted by your methoxide. That will swing on down, kick off that iodine over there, and what you'll make is, you'll get back your methanol, which is going to be sort of a wash, but also you will make isobutylene, which is, hey, it's all well and good, but it's not what you wanted to make. It's this guy here, right? It is the 2-methyl propene, which is also isobutylene. So this is not a successful reaction to make this ether. Okay, so be very wary when you do Williamson ethers that you choose the right methods to use. Okay, or the right choice in substrate. Okay. All right. Oh, this is one of my favorite ways to make epoxides. Right. We touched upon this last semester a little bit. Okay. So here you have, what do you have? Here you have this sodium hydroxide in water, and you do this intermolecular SN2 reaction to give you an epoxide. Right? How does that work? Well, pretty straightforward. You take this hydroxide here, you pull off that proton right there. This guy here swings back to that oxygen, and what you end up making is there's your iodine, and here's now your alkoxide side of it, right? All right. Then when you have that, then this undergoes an intramolecular reaction where this attacks that carbon there and kicks off that iodine, giving you your desired epoxide that you want. Okay. Now, this doesn't work all the time because you have to have the correct relative stereochemistry here and here. This has to be trans. It has to be opposite each other on the ring, right? This here doesn't work because these guys here are not on this. These are guys here are on the same side of the cyclohexane ring. No epoxide is observed. Okay. Let me draw out the active intermediate, the reactive intermediate for this to show you why this has to work that way. All right. So let me just see if I can quickly guess at the right. If I can guess at the right. You know what? I'll probably use the other conformer, so it'll be able to easily be seen. I hope. Okay. Yes. This will work out just fine. I think, right? You know what? I was probably right the first time. Let me just use this other isomer. Yeah, this was right the first time. I don't know why I screwed it up. All right, so this is one chair conformation of this, and so this iodine here can be down here like this guy here can be down here like so. So this iodine is going to be right there. Now your eyeball is going to be right up. So my eyeball here is looking at the screen, right? But your eyeball here, when you flip this guy here, when you flip it 90 degrees, your eyeball is going to be looking down on the molecule, right? Here's your eyelashes right there. Here's your bloodshot because of the because of whatever you're doing. Because of whatever, I'm not judging you. I'm not judging you. See, you're looking right down at the ring there, right? The iodine is going away from you, so the iodine is going away from you. The alkoxide is now coming up at you, just like so. There's your O minus right there. All right, and that's happening like so. You see how this oxygen, this alkoxide here, has a straight shot at the backside of that carbon? That's exactly what it needs. It needs to have, boom, right there, to have a perfect intermolecular SN2 reaction to give you your essentially your cis epoxide. All right. Now you draw out a quick sketch of this, and you'll see immediately how this can't work. Let me draw out the same exact structure, except change out the stoichiometry of this, and you tell me if you think it would work. I'll draw out even the deprotonated version and tell me what you think. Okay. All right, and so the iodine's still going to be going down, but now instead of the alkoxide here coming up, it's going to be cis to this iodine. All right, which means, well, your hydrogen here would be here, and your alkoxide would be right there. There's no way that this guy here, even if you do a chair flip, that this alkoxide would ever get a straight backside attack. Like this is a nice straight backside attack because it's an SN2 reaction. There's no backside attack on this alkoxide species, so it can't ever really be done. All right, so that's not going to be the reactive. This species here will not give you the cis epoxide that you so desire. Okay, so just keep that in mind. So even though it's a straightforward thing, you can make epoxides this way, and you can make, if you have a chain, essentially, and you have, if you have, this guy there, and you have like a straight chain here, for example, and I'm just drawing in the stoichiometry. But with a straight chain, as long as there's no rotation hindrance there, it almost doesn't even matter what the stoichiometry is here, but it will give you whatever the stoichiometry is at the very end, resulting in it. All right. But this guy here, there's no ring here to worry about rotation. But as long as you have sort of a good straight shot at the the epoxide, that's going to be overall a good thing for you. Okay. And what I will do here is I will now translate that going towards you to now this going towards you, and this going away from you to this going away from you. Okay, that's how you can do that very simply. All right, so that's one of my favorite ways to make epoxides. All right, and so we've talked about this last semester, synthesis of ethers by alkoxymercuration demercuration. All right, and so what we use here is that we use this mercuric trifluoroacetate, and normally we'd use it with just some water, right, to give you the thing that you need. Let me just see real quick here. Yeah, normally we would use this guy here to give you the what's going on here? Hold on for 1 second. All right, we are back to doing this because, all right, good. All right, sorry, I had to take a little bit of a break to deal with some dad stuff. Aw, Dad. All right, where are we here? Okay, so alkoxymercuration demercuration, okay. And so last semester we did, put this back to pen. This was an alcohol. This is a water before, and this is a way to give us Markovnikov addition without rearrangement. Okay, but if you don't use water and you use a decent selection actually of alcohols here, you can say instead of making alcohols here, you can make ethers, right? So imagine if this guy here was a water, this guy here would be an alcohol. But if you use this ROH or whatever this alkyl group is here, you can make a regular ether, which is a very a very versatile way to use to adapt this this alkoxymercuration demercuration. All right, just make sure you have both of the reagents that you need. we talked about the mechanism of this, and the only thing that you're responsible for is, let's just go through the first step here, okay? The first step that you only really have to know is, like this last step here is a little bit too much. So what we're normally going to be doing here is we're going to say this Hg is pretty much attached, right? That's a carbon, all right? There's an oxygen there. There's a carbon here. There's that. And this is what, CF3? All right, CF3, fine. CF3, pardon the penmanship thing, it's the pad and what other factors as well. CF3, all right? All right, so this is what this is except drawn out, all right? So what we do here is that we're going to assume that one of these trifluoroacetates are liberated, right, from that mercury salt, all right? And that's going to give you, I'm going to just draw it down here. It's going to give you this Hg. We'll say Hg O2 CF3, but plus, all right? And that guy here is going to pretty much, now this guy here has some lone pairs of electrons on it. We don't normally draw lots of lone pairs on transition metals, all right? But for now, we'll just do this, okay? And your book doesn't talk about a mechanism, and this is about as far as I want to go with it. This here swings on up in between that mercury and that carbon, and then this lone pair here swings on down like so, giving you this mercurinium bridge, right? That's an R group there. And here's your mercurinium bridge, all right? And once you have that, Hg, there's that, and then you have your your trifluoroacetate group on that side, all right? CF3, all right? And there's your mercurinium bridge right there, okay? And then what happens there is then your alcohol from here comes in and attacks this side, all right? So you have whatever that alcohol is here, comes in and attacks pretty much the most hindered side of this guy here, because what it's attacking, it's not attacking this carbon that's on the interior because it loves to attack hindered carbons. It's attacking the carbon, you might remember from last semester, that has a greater partial positive charge. Well, why does this have a greater partial positive charge than that? The reason why that one has a greater partial positive charge is because this guy here, if you were to think about this in terms of a carbocation, and imagine this R group here was a carbon. If you were to think about this carbon here as a carbocation, this would be a secondary carbocation, which has a greater positive character. This guy here would be a positive carbocation, right? A primary carbocation, which would have less positive character because it's a primary. You have less hyperconjugation. Here you have more hyperconjugation because it's a second. It would act like a secondary carbocation. This guy here is a primary. It would act like a primary carbocation. All right. So this guy here is a more developed delta positive charge right there. All right, to give you this. And then there, from here we don't talk about the mechanism because it's just a little bit too much for this course. But this is your reduction step. So oxymercuration here, alkoxymercuration, demercuration to give you your final overall ethereal product. Okay. All right. All right, and so this is this. I love how your book talks about this. Actually, this is a really wonderful thing. It's not just about how to make ethers from alkenes and alcohols and acids to give you a certain ether, which is what it is. But they're talking about this ether that they're making specifically as a protecting group, which is sort of wonderful. All right, sort of wonderful. All right, you always need a good. A really a nice selection of protecting groups for alcohols, all right? And this is just one of them, all right. And so how this thing happens is that this is as straightforward as it comes. You take your alcohol, you take your isobutylene or your 2-methylpropene, you hit it with some acid, and then you end up getting this protected alcohol here, which then you can do some chemistry on the other side of your molecule and not worry about this getting involved. Like for example, let's say I'm doing some base chemistry or some nucleophile chemistry on like this side of the molecule, right? And that's all well and good, but I really can't, I can't do base chemistry or nucleophile chemistry if I have a free proton around. So let's get rid of that proton. Well, I can either use Tosyl if I want to, or I could use this guy here, right? This guy here removes that proton, gives you this guy here. You can do all your chemistry over on this other side of the molecule, and then remove this later to get your alcohol back, which is pretty great, right? So this is a protecting group, just like the Tosyl group or the mesyl group or the triflyl group is a protecting group, all right? So it's not just an ether, it's that too, but it's used it's employed as a protecting group, so it's great. And it's easily removed by treating it with a dilute aqueous acid, all right? All right, you know what? Let's talk. I want to talk about that mechanism actually. All right, let me talk about this mechanism. Okay, very simple mechanism. All right, I'm going to leave that there. I'm going to take this guy here. I'm going to, we're going to imagine that this sulfuric acid is all it is just H plus. All right, so we're going to swing on out, grab that proton over there, very Markovnikov style. All right, and so now I'm going to redraw this carbon skeleton. This proton here, because it's a Markovnikov style of addition, will go to the exterior, the distal or the distant carbon here, where it already has lots of protons on it, because it wants to expose a tertiary carbocation. All right. So that's sort of the thing that we talked about last semester. If it's not, this doesn't go to the end of the olefin because of a Markovnikov's rule. That's a rule that a guy thought up. The reason why it happens is because it's exposing the most stable carbocation. So notice I'm not drawing the primary carbocation, I'm drawing the tertiary carbocation. All right, tertiary carbocation, very stable. Okay, all right. So I have that there, and now let's reintroduce our alcohol group there. Okay, let's take our alcohol group there. All right, and it's going to do what it does with its bad nucleophile self. Pop right there, giving us our there you go. Oh, positive charge. Positive charge there. Okay. So now you have this guy here. Then from there to there, essentially all it is then you take this is not just H plus. This is H2SO4, but if you remove one H plus from here, it's HSO4 minus. So one might imagine HSO4 minus. One might imagine that the SO4 minus pulls off that proton to give you back your neutral species, or you can just have water pull it off because there's plenty of water in there too. I'm sure as well. All right. All right. So that's another thing. So that's how to add on this tert butyl group too, and we've talked about this a little bit last semester, but we've never talked about it as a protecting group, and I really love the fact that your book does talk about it. Okay, so why don't you make sure and pause the video here and copy this all down, because I didn't leave myself another page after this to talk about it, but we got to talk about how to remove this guy here with aqueous dilute acid. Okay, so pause it and take this down. Or print it off, or do whatever the hell you want to do. All right, you ready? All right. Erase. All right, now let's go backwards. Let's go backwards. All right. Now we want to remove. We want to remove this thing here using aqueous acid. All right. Let's put an arrow there. Let's put a little bit of H plus here with some water. All right. We need the aqueous acid because the aqueous. This OH here is part of it. Okay. This guy here gets protonated. All right, there's that. And now, what do you think happens? This guy here, why did I just lapse into Jerry? And what do you think happens? Who are these people? All of a sudden, I'm Jerry Seinfeld. All right, this water here. Who eat all these peanuts on an airplane? How do I need? Okay, so you take your water right there. This guy here attacks the backside of that carbon right so. And now you have your alcohol back, plus your tert butyl alcohol. Okay. See, because that attacked the backside of that carbon over here. All right, giving you that species right right there. Okay, so there's your aqueous dilute acid. Now you have to use aqueous, because if you don't use aqueous, you need to have the water there to do this, this SN2 reaction. Okay, so stick that in your pipe. All right. Silyl ether protecting groups here are probably the most beloved protecting groups of pretty much everybody, both students and practitioners of the art itself. Okay, because they go off they go on very easily, and they come off just as easily. All right, and there's almost no mechanism to it. Okay, so tert-butyl dimethylsilane, tert-butyl chloro dimethylsilane, very popular chlorosilane that we can be adding on here. Silane is the atom right underneath carbon, so it shares a lot of properties of carbon actually. But what it doesn't have, that carbon, what carbon doesn't have, that Silyl does have, is that the ability to be able to expand its valence temporarily to be able to do some chemistry. All right, let me show you what I mean. All right, so this guy here comes on. Remember, this alcohol here is that alcohol. All right. So take this guy here, attach this silane right there, and what you have is this. All right, it's an addition, again, similar to before. It's an addition elimination. All right. Methyl, and tert-butyl. Okay, I know it looks a little bit weird. All right. Ugh, I'm making it worse. Just stop it. Positive here. Negative. All right, so there's your two methyls, your tert-butyl, your chloro, and there's all that business there, okay? All right, so what happens is that this guy here just pops off spontaneously. It's temporarily expanded its valence, right? The silane is not in the 2p orbital, so it doesn't have to follow the octet rule, right? The silane here pulls off, right? Pops off chlorine. Pop. All right, and when that happens, you end up making that guy there, which again should look very familiar to you in terms of like all these protecting groups. They all sort of go on very similarly. Our chlorine here pulls off there, pulls off that proton over there, and gives you the thing that we talked about. Okay, imidazole is a pyridine-like molecule that does the same exact role, that uses the same exact role as pyridine. It absorbs HCl, right? So there's that. All right, very useful, very easy to go on, and just as easy to take off. It's so sweet to take off, actually. Okay, so here's one protecting group there, and you use something called TBAF, right? Tetrabutyl ammonium fluoride, or TBAF. TBAF, tetrabutyl ammonium fluoride, tetrabutyl ammonium fluoride in THF. You do that, and it's pretty much a straight shot, right? What happens here is that your TBAF, all it is a source of nucleophilic fluorine. The same way you can also, by the way, use aqueous HF too. But aqueous HF is a bad actor. It's terrible, actually. It's very bad for you. HF. Oh yeah, it was featured prominently in Breaking Bad, for example. It dissolves people, not just people in New Mexico, but people's everywhere. All right, persons everywhere. All right. So aqueous HF is something that you can use, or TBAF. TBAF is a nice salt that you can pretty much almost handle with your hands, which is sort of nice, but you still don't want to do that. Be very careful with TBAF. All right. Anyway. It's a source of nucleophilic fluorine, and fluorine's like I just can't wait to get into the limelight, and here I am finally. Even though I remove groups, that's fine. I'm still a player. So it tacks into silane again. Zoop. Oh, I want to watch Better Call Saul, that spin-off show of Breaking Bad. I can't wait to see that. I think I missed the first few episodes of it. I don't know what's supposed to be on. I gotta see. All right. ROSI, methyl, tert-butyl. Here's your fluoro. All right. And so now you have this guy right here, right, which has this negative charge here. And this is going to break down just like it broke down before when you were just adding on the alcohol onto the chlorosilane. So this breaks off here spontaneously as this just snaps off, giving you your RO minus NH4 plus. So this, your textbook here is wrong in this respect because it asked me to do it this way. This is not right because what you add, you have no source of protons here, so you actually have the ammonium alkoxide plus your Si. Oh, I'm such a stickler. Why can't I just leave your poor textbook alone? All right, there's your terbutyl dimethylfluorosilane. Here is your alkoxy ammonium salt. If you treat this guy here with water or whatever the hell, whatever, some proton source, then you get, H plus. This is H plus. H plus in water. There you go. There's your alcohol back. As soon as you're done with it. But if you don't treat it like that, then you have your ammonium salt back, which is a big mess. All right. All right. So my question to you is that why the hell does it go this? Why does this reaction go this way? Why does it kick off the OR versus the why does it kick off the SiO bond versus the SiF bond? All right. What I'd like you to do, and you can just Google this on the interwebs. Look at the bond strength between silicon and fluorine. Silicon and fluorine are one of these bonds that are like made in history. Silicon. Let's give you an example. To harden the enamel in your teeth, you use toothpaste with sodium fluoride in it, right? Well, your teeth are essentially made of silicon oxides, and fluorine in the toothpaste is very much attracted to the silicon bond because the fluorine silicon bond here is one of the strongest polar covalent bonds known to organic chemistry. So this is a very, very, very short bond and very energetic, and it will kick off anything else to maintain the silicon fluorine bond here. So this guy here is a very favorable bond. All right, so that's why that given a choice, it will kick off the next best thing because it is not breaking that bond again. Silicon fluorine, very strong, so strong that we use fluorine in our toothpaste to harden the enamel of our silicon-based teeth. All right. That water. There you go. Okay. All right. So this is something that I might save until afterwards to talk about. In terms of the why would we use this, why would we use these kinds of things and these procedures in the syntheses, why would we use these these protecting groups here? So for example here, why don't you make this molecule here from that guy here and this guy here? Well, if you just take this guy here and you treat it from here to here, you won't make this, right? You won't make this. You will deprotonate this guy here before you'll displace that. So this will happen, right, to give you 1, 2, 3, 4, right, plus that sodium alkoxide bond here will be made long before that's made. Because this all acid base chemistry, as you know, is faster, all right, than anything nucleophilic, all right. So there's that. You want to make sure that you understand that, all right. So what do you do to make this? How can you treat this problem? Well, this is where you can either use TBS chloride. You can use what the hell you want to use? You want to use TBS chloride? You can use isobutylene and acid. You can use tosyl chloride, whatever you want to use, right? But TBS is so TBS TBS chloride is so any of the solid chlorides are so easy to use and so readily taken off. Then this is just the best way to go. Take TBS chloride, treat it with this guy here. This TBS will go onto this oxygen here, protecting it. Then you can do all the SN2-like chemistry that you want to do without worrying about anything else. And then at that point there, this guy here attacks the backside of that carbon over here, kicking off that iodine, giving you that guy right there, and then TBAF it, and then you can get this guy here, right? So you need to use this step. This step here, even though it's a protecting group here, is one of the most important steps in doing any of this chemistry. If you don't have that, then there's no way that you can actually produce the chemistry. All right. Reactions of ether. We've talked about this a little bit before. If we've taken an ether here and we hit it with HBr or especially HI, they end up cleaving. All right, they end up breaking in half. Okay, so here if you take it with HBr here, you make an oxonium salt. All right. Again, very nucleophilic, very basic, that will attack with anything that is either electrophilic or acidic. All right, that's what this is. So all acid-base chemistry is here. Like this is a base, this is an acid, right? Period. But if you look at it a different way, this is actually sort of a nucleophile. This is actually sort of an electrophile, right? It makes that's why I make such a big deal about acid-base chemistry in the very beginning. Not because I'm some sort of a weirdo wonk about acid-base. I could give a shit. I just want you to know that acid-base is the reason why everything ever happens at all. All right. So there's that. So, all right. Let us talk about the cleavage of ethers. Okay. But instead of using HBr, we'll just use HI. I'm going to do two of these guys here. I'm going to do this guy here first. HI, hydroiodic acid, a very, very strong acid. All right. This guy here grabs that proton right here. All right. All right. And there is your iodine right there. There's your oxonium species there, plus your iodide right there. Your iodide there is now a good nucleophile, which would attack the backside of that carbon right there, because this guy here is a good leaving group, right? So this carbon right there has a slightly positive charge, which attracts that iodine. We're like, yeah, but big deal. This has a full positive charge. Why doesn't that attack that charge over there? Again, not productive. There's nothing it can do with that. It could because this is acid-base chemistry. It could certainly go backwards. So it could pull off that proton and then go backwards because it's acid-base chemistry. And whenever we draw acid-base equations, we should draw the double arrow. But in this case here, we didn't, because we know we want to go forward to do the chemistry. So just shy of going backwards, let us attack nucleophilically this carbon over here, because it's now electrophilic. Because if it's electrophilic, because it knows if this oxygen gets this pair of electrons, it will then no longer be positive, which is the oxygen's motive to help this reaction to go. Okay, so this reaction attacks. So this iodine attacks that carbon over here, like so. Bloop. All right. I don't know if it actually makes a bloop sound. That just might be me being a Foley artist. I don't know. I should be a Foley artist. All right. Let's draw exactly what we draw there, like so. All right. This, and we'll put the iodine over there. Okay. So, but we're not done. We're not done, right? Because this now we've made one ethyl iodide, but we still have this alcohol lying around. And the way this reaction goes is that this guy here, you have to have all the equivalents of ethyl iodide. Okay. So let's just attack it with one more mole of zoop. And just like before, attacks the back side of that guy over there, like so. Kicks that off. The same exact reason for that, right? And it gives you another mole of ethyl iodide. So now overall, you have your overall reaction mechanism, the overall scheme, using hydroiodic acid is that 2 moles of that stoichiometry-wise, and whatever else do we make? We made we made water, right? Plus water. I believe we made 1 mole of water, right? Yep, 1 mole of water. So 1 mole of diethyl ether plus 1 mole of HI gives us 2 moles of ethyl iodide plus 1 mole of water. Okay, that is the full mechanism for the cleavage of standard, regular, simple ethers. There's a little catch, right? Remember, all the steps here, there's nothing special about the cleavage of ethers that make it like, well, that has to go this way. No, all this is acid-base chemistry SN2 reactions, acid-base chemistry, SN2 reactions, boom, there you go. There's nothing special about this reaction, this overall scheme that makes it any more special than anything else. All right, so it's still governed by the other strictures of standard substitution chemistry. What do I mean by that? All right, let me show you an example. You take phenylethyl ether. Hit it with HI. Hit it with HI. All right. Boop 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 boop. Wow, that doesn't even look like. Uh-oh. HI. All right. So there's that. All right, there's that. I'm turning off my phone because I have a funny feeling I'm going to be getting some messages. All right. Boop, 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 boop. Okay. Plus. All right, so there's that. There's that first acid-base reaction that happens, right? Now you have iodine here that attacks the backside of this carbon species right there, like so, giving us this guy right there. OH. Okay. All right. And so now, plus this guy here. All right. All right. Now, normally, if this is a regular ether, I'd say, well, now you go and do it again. Now you protonate this guy here and then the whole thing. But this is where the reaction stops. Why is that? The reason why is because you cannot protonate this phenol and then do another backside attack of this. Why? That carbon is sp2 hybridized. There's no such thing as an sp2 hybridized carbon undergoing an SN2 reaction on something like this, or on anything actually for that matter. Okay. So the reaction is done right here. Again, nothing special because of ethylphenyl ethers or whatever. It's just the chemistry doesn't allow it to go forward. All right, that's all it is. Okay. All right, let's go forward. Come on. Undergo reaction in which carbon oxygen. Okay, so we talked about that's just a cleavage of the ethers. Okay, and so you can use that with HI or HBr if you want to. No big deal. And I don't know if HCl is strong enough, but I know HI is. So anyway, and there's a mechanism if you don't want to see all my scrawling. Although I do think my drunken scrawling is fun. Epoxide. Okay, epoxides. We love those. They're very straightforward to make, more or less, and they're very nicely reactive. Okay, 3-membered ring containing an oxygen. All right, how do you make them? Well, you can make them with a peroxy acid. What's a peroxy acid? Well, if you had a regular benzoic acid, this would be a benzoic acid, which is a regular. Is a regular carboxylic acid, all right? And it just has 2 oxygens and 1 carbon, and it makes it a carboxylic acid. But if you have a per acid, per means more, or peroxy acid just means more oxygens. That means you take your regular carboxylic acid, then you add on 1 more oxygen in between the carbon and the OH. So this extra oxygen makes it a per acid. Or peroxy acid, okay? Like MCPBA, or this regular methyl peracetic, this peracetic acid. Acetic acid comes from the acetate ion right here. The per comes from this. So here's your peracetic acid right there, and here's your metachloroperoxybenzoic acid, okay? The mechanism from this olefin to this peroxide is one of my favorites. You are going to love this, all right? All right, so we will talk about, oh, come on, give me a clean, oh, okay, we'll talk about the stoichiometry, and then we'll give you one quick mechanism, okay? So Here is if we have a trans olefin or trans alkene and use MCPBA, then we have a trans epoxide. Why? It's not because what's going to happen is that this oxygen is going to come from one face of the double bond. Instead of drawing the trans bond like this, let me just draw it like this. Let's draw it like where it's flat like so. And if I'm pivoting this towards me, where this is a little flatter, where this is in the plane of the paper, and I pivot this towards me and then that away from me, what happens, it looks sort of like this guy here, like so, all right? All right? So this is going away from you, this is coming towards you, and you are lowering pretty much the oxygen in the plane of the paper to give you this guy here, right? So if you start off with a trans olefin, you end up with a trans epoxide. You start off with a cis olefin, you end up with a cis epoxide, all right? And just keep this in mind, more electron-rich double bonds react faster. So if you have two double bonds and use MCPBA, which is the standard reagent to do epoxidations, then you will have the epoxidation happening on the more electron-rich side. This side here is more electron-rich than this side because you have methyls here dumping some electron density into that olefin side. Okay. Okay, so let's talk about the mechanism finally of this beautiful reaction. You're going to love this, all right? And we'll actually use the trans epoxide to start with, okay? And we use MCPBA. But let me talk about MCPBA for 1 second. Here's metachloroperoxybenzoic acid. Here's how you normally draw it. Metachloro, ortho, meta. So here's, all right? And how we're going to draw this, though, we're not going to draw it this way when we look at the mechanism. I'm going to probably just do this. I'm probably just going to say this guy here is going to be phenyl, because I'm just going to abbreviate this because our transition state is going to be so very clogged up. It'll be very congested. Because I care about the configuration or the conformation, believe it or not, of these 1, 2, 3, 4, 5 atoms right here. We will not be drawing them that way. We'll be drawing it, and I'll just do one, so I'll put that as phenyl now. We're going to be drawing them in a very certain, very specific way. We're going to be drawing them such that they look almost like a 5-membered ring. 1, 2, 3, 4, 5. I want them to draw in this way, right? Why? Because I want to get at that oxygen right there. This oxygen right over there. And I also need that oxygen to be close to that proton right there, because this is going to help us be the linchpin of this entire reaction mechanism, okay? Let's start off with a very simple olefin. All right, we'll start off with just ethylene gas. All right, ethylene gas, hitting it with MCPBA will give us straightforward epoxide, right? Oxirane. All right, the mechanism. All right, and I believe it's methylene chloride. All right, so I'm gonna draw it out a little bit on the. You know what? I'm gonna draw it out a little bit on the big side. All right, I'm gonna draw it on the big side there, and you know what? All right, so copy this all down. All right, I'm gonna use a clean page because I want to make sure that we have a nice clean palette to work with here. All right, so here's your overall reaction mechanism. All right, CPBA gives us oxirane. Okay, so what's the reaction mechanism? Nice and big. I'm going to draw it nice and big. All right, so there's our expanded olefin, and here's our MCPBA, but drawn in that really weird way where we have the oxygen, right, isolated, right? All right, and so I'm going to do that. I'm going to do that. All right, and have that there. And I'm going to have that right there. And I'm going to abbreviate again the phenyl for that. All right. I drew this oxygen here outsized for some reason just because. All right. Now what's going to happen here is that this pair of electrons here is going to help me out here. Right. This guy here is going to help me to pull off that proton here, which will help break this bond. This pair of electrons here will attack that side of that carbon-carbon double bond here. When it does that, this bond here will flip on up and attack that oxygen over there. When it does that, that oxygen will then at that point be breaking the octet rule. So it has to fulfill the octet rule by breaking this oxygen-oxygen peroxy bond over here. Then when that happens here, that bond here comes flipping out there, and then that kicks up like so. Okay, let's show you what this means. Okay, so that pair of electrons here grabs that proton right there. This pair of electrons here slides on down, crashes into the other side of that. Now this already has as many electrons as it likes. All right. So that means one of these double bonds here cannot be that way. All right. So this will then flip on up like so. And the way the style is, I'm going to put this pointing to like almost nothing. Like you'll see here where it looks like I'm not pointing to anything. Well, I am pointing to the imaginary bond that will be formed when we make the epoxide. Okay, that's a style of this mechanism. All right. All right. So that swings on down, crashes into that. This swings on up between that oxygen and carbon bond over here. If I form this carbon-oxygen bond over here, I am breaking the octet rule for this oxygen. So I have to break this peroxy bond here. All right. When I do that, I'm just going to dump this pair of electrons in between that oxygen and carbon bond over here. And when I do that, that'll be great because as you remember from the beginning, this oxygen here is protonated, so that O is going to be an O+. And that O+ does not want to be that way. That oxygen does not want to be electron deficient. So if I were to dump this electron density in between this oxygen carbon bond here, then I can swing this up here and make that oxygen neutral again. Let's now unravel this mess and see what we have. It's almost like the unexciting part is the epoxide. So there's our epoxide that we've just formed. And now I'm just going to draw this as per, just written just like that. All right, so here's your phenyl. All right, so now the bond comes out. Now this carbon bond over here is not going to be a carbon oxygen bond. Is going to be carbon oxygen bond here, but it's going to be a double bond because this bond over here is a double bond. And then this carbon oxygen bond here, carbon oxygen, is going to be a single bond. And then this oxygen here now has a hydrogen on it. It's going to be that hydrogen right there. All right. So now we've made, with MCPBA and ethylene gas, we've now made oxirane and benzoic acid. And this benzoic acid can be washed away using acid-base chemistry. Acid-base washes it in a subfunnel. All right. So that's how it. So this is the mechanism for MCPBA. There's only one crazy little transition state, thing. And that's what that, and this is what it is, okay? So here's what I need you to do. I need you to practice and practice and practice this. It's not immediately obvious to you, but once you start doing a few, just practice this mechanism. And when you start doing a few more, you'll see how it'll ultimately make sense to you. It's like, oh yeah, now I see how this guy here helps this bond here to form this guy here, for example, right? Because this guy here pulls off that proton, makes this nucleophilic, then crashes into that, and then this is already filled up with electron density. It's already obeying the octet rule here, and it swings on up, but it's going to start to help to break the octet rule with that oxygen over there. And you see how that's not going to work out. All right, so again, practice. Okay, this is all it is. All right, how many times, so for you new people, how many times should you practice this? Some of you get it on the first 30 tries. Some of you get it on the first 75 tries, right? But keep on trying. Frustration's a part of it, right? You have to make sure you give yourself the frustration. If you're not frustrated, you're not trying hard enough, okay? For those of you who have got it, make sure that you can use as many, do as many problems as you need to feel comfortable with it, okay? I love me some MCPBA. It's one of my favorite reactions. All right. So the high-strain three-membered ring of epoxides makes them much more reactive towards nucleophilic substitution than ethers, than other ethers. All right. So here's an acid-catalyzed ring opening of an epoxide that you might imagine. So you have an epoxide that you've made by either by MCPBA or by the base chemistry using your iodine hydroxide thing. So either this way here, or this way using MCPBA. Okay, so either way. All right. So now you've made your epoxide. Now you want to open it up and do something with it. Okay, fine. So let's take our epoxide and hit it with some acid. And once you do that, this guy here, right, this guy here will protonate, right, from that acid there. Then these guys here become very electrophilic. Why? Because that oxygen here does not want to have a positive charge. So this guy here, of course, you you have an alternative. You can either go backwards, right? But we've talked about not being productive, or you can go forwards, which is what we're going to do because we want to make the reaction go. All right. So we have our water attacking one side of this epoxide versus the other one. As long as you break that carbon-oxygen bond here to fulfill, to have oxygen have its octet of electrons back that it wants. All right. So once that happens, water will then come in and pull off one of the protons from the resultant nucleophilic attack. So this water here attacks the backside of that carbon over there. All right, so keep an eye on this water right there. That water right there is that water right there. Another mole of water comes in, grabs a proton from there, neutralizing it and making this diol. This diol has a very specific category of diol. It's called a vicinal. A vicinal diol. A vicinal diol is a diol in which you have a 1,2 diol situation. You have two alcohols on adjacent carbons. Okay, vicinal diol. Vicinal meaning in the vicinity or close. It's also abbreviated as a vis diol. Okay, so here's your vis diol thing. Okay. You can even do a base catalyzed ring opening of an epoxide, right? And this guy here, your book chose to use an alkoxide version of this, but you don't really have to. You can use either an alkoxide or you can even use a hydroxide. There's no reason why you can't do that to give you another vicinal diol. But yeah, this is just straightforward, straight up attacks one of those sides, one of those carbons here. Of course, there's no protonation because it's a base catalyzed. And then once you do that, then this guy here, opens up. Right, giving you the alkoxide there, and then you have the alkoxide here that can't just be this way forever because it's unstable that way. So you have to protonate this in some way. The only proton source you have there is from some alcohol source that is maybe your solvent, perhaps. All right. So there is your. So for example, like here, if this is like methoxide, you're probably running the reaction in methanol, right? Then this would be the methanol that you would use, okay, to be able to pull off that proton there to give you your vicinal. Well, it would be your alcohol ether. But again, if you use an hydroxide here, then you'll have a vicinal diol with your alkoxide there. Okay. Okay, folks. I think my kids. I have to go to sleep, and so my wife told me I can't be blathering on anymore. Anyway, thank you for this. Nighttime edition of Organic After Dark. Mwah. I don't know what I just did. Anyway, night-night.